Okay, so now we're going to move on to oblique impact. In the previous videos, we've looked at central impact. Okay, and remember, central impact is just simply if you've got a collision between two particles, and we draw the plane of contact, okay, between those two particles. The line of impact is a line that is perpendicular to that plane of contact, and the line of impact also passes through the centers of mass of each particle. Okay, so the line of impact is perpendicular to this plane of impact, plane of contact, and the line of impact passes through the centers of mass. Now, if the particles are both, if particle A's center of mass is moving along the line of action towards particle B, and particle B's center of mass is moving along the line of impact, then that is central impact. However, if particle A's velocity, which is moving in this direction, is not along the line of impact, and or particle B is moving at an angle to the line of impact, then that is called oblique impact. Okay, the velocity of the centers of mass are not along the line of impact. Okay, so that is the first kind of basic definition or description of oblique impact. Now, how do we analyze? So what does it say here? The next thing that I want you to pick up is that our assumption is that these are smooth particles. Now that is very, very important. Okay, so take that into account. They're smooth particles. And okay, so I'll get back to that in a minute. Just take note of that. That's very important. Then the next thing is we often want to find information right after collision. Okay, and oftentimes, so as you can see with this one, the two particles come at each other at an angle, they collide, and then they move away from each other again at an angle to the line of impact. So this is the information that we're looking for, that we have: initial velocity of particle A, final velocity of A, initial velocity of B, final velocity after impact. And then you've also got these angles, okay, to the line of impact. So these are all the things that we often want to try to solve for. Okay, now what are the concepts that we need when we're trying to solve for this? Well, if we break up this system into the two particles and we analyze just particle A, we will see that initially at state 1, particle A has both a horizontal and a vertical component of momentum. So momentum, it has a horizontal component, an X component of momentum, and a Y component of momentum. Then an impulse, remember, mv plus sum of the impulses is, so mv1 is mv2, right? That is linear impulse and momentum. We're just considering a single particle. So it has an initial momentum in the X and the Y. Then it has an impulse that particle B applies to particle A. There's an impulse. Now, what do you notice about this? It's going at an angle, but we're only considering an impulse in the horizontal direction. Where is the impulse in the vertical direction? See, that is a very key point that you need to take note of. Our assumption is that the particles are smooth. The only time that a particle would experience a vertical impulse during contact is if there's friction between the two particles. Okay? If there's friction between the two particles, then we do need to consider a vertical impulse. But our assumption is that they're smooth, so the only impulse will be something that's normal, perpendicular to this plane of contact. The impulse of B onto A. Okay? So we have the initial momentum in the X and the Y, plus the impulse only in the horizontal direction from B onto A. no impulse in the vertical, equals the final momentum, which is going to be a x component and a y component of momentum. Similarly, I'm not going to spend much time on this. B has an initial y and x component of momentum. Then it has an impulse only in the horizontal direction, no impulse in the vertical. Because why? Because it's smooth. And then it has a final momentum in the x and the y. Okay? So those are the assumptions that we need to pick up. Now, how are we going to solve, say, for these final velocities? Again, we need to break things up into its x and y components. So let's have a look at this. Procedure for analysis of oblique impact. I'm going to read through a lot of this because it's very helpful. We need to first establish the y-axis. The y-axis is just if you've got two particles colliding, the y-axis is just, oh dear. Okay, but you get the idea, right? One day I'll get a better tablet and then okay? So that's the y-axis. It is the plane of contact, okay? Now listen. We need to establish also the x-axis, which is the line of impact, okay, which is perpendicular to the plane of contact, and the x-axis passes through the centers of mass. Listen, the impulsive forces of deformation and restitution act only in the x direction. Okay, we've spoken about this. These only act in the x direction because the particles are smooth. But now, by resolving the velocity or momentum vectors into components along the x and y axes, it is then possible to write 4 independent scalar equations in order to determine the final velocities of each particle. Now, check this out. The first very important thing is that momentum of the system is conserved along the line of impact. Okay? The two particles they're coming at each other, they collide, and then they move away at these angles. If we consider the system and we consider just the x direction, then momentum is conserved in the x direction. Why? Because these impulses are internal. So momentum is conserved along the line of action, the x-axis. So the momentum in the x direction is equal to the initial momentum in the x is equal to the final momentum in the x. Okay? So that's the first thing. Second thing, remember our friend, the coefficient of restitution. Notice, it relates to, okay, I'm not going to go into what it is, but my point is we can apply the coefficient of restitution in the x direction. Okay? So the final velocities divided by the initial velocities. So the coefficient of restitution is applied only in the x direction. Then we can take these two equations and solve simultaneously to find these final components, these final values. Okay? Now, a couple more interesting things which are very, very important is that because there is no friction, we don't have an impulse in the vertical direction. What does that mean? Guys, what does that mean? It means that the velocity, the momentum of A in the vertical direction does not change. And the momentum of particle B in the vertical direction does not change because there is no impulse in the vertical direction. So what our next assumption based on having smooth particles and there being no vertical impulse is that the velocity of A doesn't change in the vertical and the velocity of B doesn't change. Okay? So momentum of particle A is conserved. Momentum of particle B is conserved. The velocity of A in the y direction stays the same. The velocity of B in the y direction stays the same. Okay? So make sure that you understand this little green little paragraph. Make sure you understand that we're going to apply these in the next video.